All right. So this is quantum mechanics 101, right? It's going to feel like that after a few minutes. All right. So this is coding one. Um, Out of curiosity, how many of you have ever coded at all before? What languages, what experience, what have we done? Somebody go ahead. Java, Python for how long? Doing what? Is this self-taught? Is this high school class? Is it? Okay. So you're basically a new beginner, never seen code before. All right. Anybody else want to share their voyage? No. It's like, well, that guy basically had a decade of coding. Don't worry, it will still challenge him because all the stuff he learned is out the window now. Um, I'm Mike Littman. I'm the chair of the computer science department. I've been here for 20 years now. I've been teaching for 26 years. This is my side gig. I run software companies. Um, I'm a serial entrepreneur. I'm an angel investor for CU Ventures. So I invest in companies. I'm currently working with 5 different startup companies. One of them's was actually spun up out of the AI and quantum lab here on campus. How many of you have been by that room or whatever? You're going to get introduced to the tools that are in that room. I assume none of you are paying like the $200 a month for ChatGPT or Claude or any of that stuff. Any of you paying the $20 a month for ChatGPT or Claude or any of that? Okay, you're going to learn a lot about that stuff today. Now, first of all, honestly, you are probably coming into computer science at one of the most exciting times in history. Legit. And I'm going to tell you a little bit about that today as we get into it. Um, my research area is quantum computing and AI. I also, well, here, let me just get to the slides thing here. I got a bunch of links up here. If I don't paint by number, I go ziggy zaggy all over the place. All right, so for starters, I record every one of our classes. So it would always be recorded. I put it up on YouTube. Here's the link. I'll link it on Canvas too when I remember. But the slides are linked on Canvas. So you can always get to these slides. Just go to Canvas, click on it's under modules. I think the Meet Your Professor, whatever. There's a thing called slides. This is slide 2 on that guy. So I do always record all the lectures and I record through Zoom. So I actually open up a Zoom session for every class. I don't take attendance. I don't care if you're sitting here. I would encourage you to physically be sitting here. That way you can ask questions in real time and stuff like that. But the lectures will always be up there. Okay. You're all adults. You get to make your own decisions. I'm not going to lose sleep over it. So you can decide if you want to come here or you want to watch on Zoom. Both of them will be going each time. Even when you're here, I would encourage you to connect to the Zoom meeting. I guess this room is maybe not quite as deep, so maybe you can all see this pretty well, but we're going to do a lot of live coding in here. So you may actually find it easier to connect to Zoom where I share my screen so you can see the code on your own laptop screen while I'm coding here. Just turn your sound off so there's not all that crazy echo stuff going on. That would be my recommendations. So, because there's just going to be text up here in some cases, I will make it as big as I can so I can see it, which will already be too big for you. But in any case, those are a whole bunch of options. The book is an online book that takes you through the 16-week sequence. For the first couple weeks, you're actually going to be working through the book and learning some stuff that I'm not even talking about in class. I'm going to be doing some background computer science-y stuff, and then eventually the two come back together once we start diving into code in here. But you're going to start seeing it externally, and the book has the information in it that you'll need to get up to speed, get your tools going, and all sorts of stuff like that. All the code in here, I have you do through online GDB. It's a website for you to, write programs and stuff like that. If you've already coded for a while and you know how to use GitHub, you can use whatever tools you want. Ultimately, the thing is when you submit your homework, I want a link to your code. I don't want a zip file. I don't want you attaching 20 documents. A link to where your code lives. Online GDB has one that has a button that says share. You click that, you copy the link in there, you're done. If you want to use GitHub, you can go and do all that stuff. So this is not a difficult thing, but just know that ultimately I want a link. I do run a Christian ministry called Quantum Disciple. That's the quantum connection thing. Let me just open this. So, and if you go to that site, I have a daily podcast. We have weekly podcast. Actually, both these come out daily as well. Oh, I have a coloring book for some of you. I think you might. So anyways, this is a Christian apologetics site. Many of you have heard of the word apologetics before. What is it? What is apologetics?
Defending your faith.
Okay, defending Christian faith. So you see the guys on YouTube and stuff who are out there on college campuses, they have the people walk up, ask the questions that everybody starts yelling and fighting over, that kind of crap. Yeah, it's not the kind I do. So I'm a scientist, and I defend Christian faith through science and logic. When you first meet someone, you don't start saying, have you learned about your Lord and Savior Jesus? And you start slapping them in the face with Galatians or something like that. No, I'm a lot more down to earth with some of those things. So my wife and I are both certified Christian apologists. So this is my ministry outside of here. I'll be giving away a lot of free stuff here on campus. There's a book called I Don't Have Enough Faith to Be an Atheist. And I have a whole bunch of copies in my office. If that would be something that would be beneficial to you, see me. I'll give you a free copy. We also have Kindle links if you prefer to read it on Kindle. Don't waste the book or waste the link. If you're not going to use it, don't ask for it. But if you or someone would benefit from that, come and see me. I'll get you a free copy. I could also get you a free copy of those coloring books. Saw a couple of eyes here. I noticed that some of you were noticing my shirts. I wear crazy shirts every single day, literally, and I'm on these, right? Where am I? On this somewhere?
Yeah.
Oh, I'm on the back. And there's this little guy on there too, right? All right, so this is where, and my psychiatrist knows about all this. So there's this little doll named Mr. Gonzalez. He's an elf on the shelf. About I don't know, 11 years ago, our cat, we had 3 cats, and our last cat died, and our big fat cat Gracie that was my kitty. I gave it a whole personality and all that stuff. Also, I was sad. My wife says, "Oh, I want an elf on the shelf." So she gets me this elf on the shelf, and that was supposed to replace my kitty, right? Also, I give him a name. I call him, "Oh, this is Jesus Gonzalez." And I said, "Oh, Jesus." No, that's not how he pronounces it. He's actually from Toronto. There's this whole backstory. You can ask students from 8 years ago, they know the whole thing. It's bad. But anyway, so you can't call your doll Jesus. So that's why we use the more formal Mr. Gonzalez. He actually has Concordia business cards that say Reverend Dr. Gonzalez on it. Well, I can do that because I run the department. New hire, right? Well, anyways, so that's who that guy is. So he's on all the shirts as well. Yeah, and he'll come up a lot of different times, but these are actual recurring actors. Well, Mr. Gonzalez stars in our children's books on my ministry. So we have here Mr. G's time machine coloring book. You're gonna load. There you go. Look at that guy. See, wouldn't those be fun? And the interesting story here is, so my art director from here, Megan, she was an atheist, very against everything. I hired her when she was an atheist, so she was actually designing stuff for our Christian ministry while she was an atheist. Well, now she's a believer, and she's actually the star in one of our shows called The Skeptic and the Disciple. She's the skeptic. But anyways, kind of interesting things. So if that's of interest to you, this is a link there. I encourage you to go check it out. Check out our Facebook, blah, blah, blah. I have a lot of research stuff on here, papers that I've written in this. And I have them broken down into like college level classes, like 100 level, 200 levels. So, like early ones might be, like learning about the other religions and how do I know God is good, that kind of crap. So each one of them is a paper. You can also listen to it. Um, so anyways, something for you to check out if you are interested. Here's the link to these presentations. Don't write this down because like I said, there'll be a link on Canvas. It just says slides. That'll take you here. All right. Zoom link is there. I'll start Zoom before every class. I'll record. Make sure, in fact, while I'm saying this out loud, okay. Oh, there's somebody.
That's me.
Oh, it's you. Okay, thank you. If you log into Zoom with your CUW, it'll automatically let you in. You won't get thrown in the waiting room. Just FYI. But if you're ever in here and you're in the waiting room, just yell at me. I'll fix it. Also, if you're online and well, it won't work in here since you're going to be muted. But if you're online and you're at home and you don't hear me, unmute yourself and yell to let me know that I have myself muted or something. Because I'm yeah, just that's it. So there's my email address. So you can email me if you have any questions, comments, concerns, bribes, anything like that. Okay, grading for the class. Just to get that crap out of the way first. Half your grade is assignments, projects, things like that. Half your grade is exams. So 50-50. There will be a midterm and there'll be a final in here. My policy is if you do better on the final than you did on the midterm, I'll replace your midterm exam score with whatever you got in your final. So if you get into the midterm and you suck and you get a 25%, you can still do well in the class. That should be your coming to Jesus moment where you decide, okay, well, why did I do poorly in this? Did I not put in the effort? Is this not my cup of tea? Yada, yada, yada. But at the very least, you do poorly on the midterm, you're not completely destroyed for your grade. You have a chance to undo that bad day. The homework assignments are meant to prepare you for the exams. So I typically grade homework fairly easily, let's say. My idea here, and you'll see if you've already clicked on the link for the textbook, is that computer programming is like a sport. You can't just academically learn. Like, for example, who plays a sport in here? All right, what sport do we play? Basketball. Okay. So, okay, we'll use this. We'll use basketball as an example. So if you spent a weekend with Michael Jordan, he taught you how to, shoot the fadeaway, right? Are you ready for the NBA at the end of that weekend? Oh, come on. Yeah, it's 118. Coding one?
Yes, sir.
All right. So at the end of that weekend, you're not ready for the NBA, right? You got to put in 10,000, you got to shoot 10,000 fadeaways before you're even close to being ready to go. You're playing college basketball, so you didn't just pick up basketball last week. You've been doing this for years and years and years. All right, so coding is like that. Somebody can academically teach you how to write an if statement or a for loop or whatever. And until you've written 10,000 of those or more yourself in the context of solving a problem, you're going to still suck at programming. It's going to be a reality. So keep that in mind as you start doing this stuff. If you've never been exposed to coding before, and that's the assumption I make, I assume that you've never seen code before. So don't feel like you're at a disadvantage if there's people in here who've had some programming classes and stuff. Because generally programming, I think, is poorly taught. If you've put in your own reps outside of like the class or something like that, then maybe you've gotten to a decent place. But generally speaking, programming is taught kind of like math, which is also taught poorly. When you're in school, you never get a context for why the heck am I learning how to do an integral? How many of you have had calculus? Okay, you have calculus. So Calc 1, what did you learn in Calc 1? So this guy hates math. You can tell, right? Yeah, that's the enemy. Go ahead. What did you learn at
Integrals and derivatives.
integrals and derivatives? Okay. So usually Calc 1 is derivatives, Calc 2 is integrals, but there might have been some overlap, whatever it is. Okay, what's a derivative?
It's like the slope of the original equation.
Okay, so slope of the tangent line at the point that that equation points to. Okay, what's an integral?
It's the reverse of the tangent line. It's going back to the original equation.
Okay, yeah, completely wrong. Yeah, that guy. So an integral is the area under the curve at that point.
Yeah,
No, it's okay. It's okay. I expect you to suck at this because remember, you had a bad teacher.
no, I had a good teacher. I forgot I was there.
Oh, no, the teacher. I'm telling you, it's okay. All right, because now we're going to see. We're going to see how good your teacher is. All right, so now everybody, we're on the same page. Derivative, slope of the tangent line at a point, and the integral area under the curve at the point. You draw this curvy thing, right? So you got the area under there, and you got the slope of a line at the above of that. Why? Was it just to like hurt you, like give you mental?
Yes.
Yeah. You see, this guy's got PTSD from it. Okay, so what do you need to know those two things for? Go ahead. Yeah, but why? Like, what are so you're using the integral for total distance when if you're if you're going up and down and things like this, but what is the integral actually used for in a real life problem, and why is an integral the solution to that? What we're doing is we're saying I have two tools. I have one tool that gets me the slope of a line in a place. I have another tool that gets me the area under the graph, the curve at a place. And we say, well, why do we need those things? Well, how many of you know how to take the area of a square? Length times width, right? So that's a regular shape. Okay. Right triangle, 1/2 length times width, right? Okay. So we have, then you have your circles, we got that. So we have our general equations for taking the area, how much space is inside of these regular shapes. But what if you have an irregular shape? Like you have an X and Y coordinate, and then you got this curvy dude there. And you say, you draw lines at the other end, and you got this weird, crazy looking shape that doesn't have a name. And you want to know how much space is inside that shape. That's what derivatives and integrals solve. They say, an integral says, what's the area of this infinitely tiny sliver at this one point in space? And so if you think about it, you draw a rectangle. Okay, so you're inside this curve, you draw an infinitely skinny rectangle at one place. All right, so the rectangle is going to be flat at the bottom along the x-axis, right? So it's sitting there flat at the bottom. So you draw your rectangle up, and then you close it at the top. You have one little problem. This was a curve, right? So at the very top of that rectangle, what are you going to have? Well, you have the curve here, and you got what does that guy look like? It's a triangle thingy, right? That guy's like a triangle. And if you know the slope of this line, you can calculate the area of that triangle. Area of that triangle plus the area of this rectangle is the area under the curve of that place. Right? You have infinitely small slivers of that, and you take the area of this sliver plus the area of this sliver plus the area of this sliver, so yada, all the way to the end where you're calculating it to. You add all those up, you have a very, very, very good approximation for the area that is under that crazy looking shape. That is what those two courses are about. And then applications of that. But because it's never put simply like that, you just think you're solving puzzles. Like, here's this integral, here's this integral. Then they throw the cosine, sine, tangent stuff at you, and this guy, head just exploded. He almost dropped out. He's like, I did drop out. He's paying his teacher off. So, all right. So anyways, coding is not something that you just crash, like you just study for the night before. If you have not put the reps in, it's not going to click. All right. But we have to have an application for why you're writing the code. I can't just say, oh, go write a for loop 100 times. That doesn't mean anything. All right. So you have to be able to solve different problems and apply these things to the solutions of those problems for you to get practice. Because it's not just about how do I do something, it's also about when do I do that. All right, so I want you to think about everything in here. You could apply this to your other classes too, like math and things like that. You have this toolbox. You got derivatives, you got integrals. In here, you have if statements, for loops, variables, yada, 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 a whole bunch of other stuff. So these are tools that are in your toolbox. And just like if you were like building a house, you want to pick up the right tool for the job, right? If you're doing framing for a wall or something like that, you're probably not going to get out the paint gun, right? You're still building the wall before you're ready for that. So you use the right tool for the job whenever you're solving a problem. We've been doing this our entire lives as humans, right? That's the problem. That's why people find computer programming difficult. It's because we have spent our entire lives working with other people. When we solve problems, as long as we understand it and we can articulate it to other people, like, oh yeah, you just do this, 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 and this, we're good at that because we spent our entire lives doing it. When you get into programming and you're just starting, you'll feel like, okay, I can't do any of this. And it's not because you're stupid. It's because you're actually too good of a problem solver. The issue is that when you solve problems as a human, how many of you, when you were walking to class today, bumped into any walls while you were walking? This guy did it on purpose. Little ziggy zaggy. Okay, but generally, you watch the students in the halls, right? They're on their cell phone, they're looking, they're bobbing and weaving in and out of people. Just it's not even worth their attention to pay full attention where they're going, right? As soon as something comes into that peripheral there, they'll do the little ziggy zaggy, whatever. Okay. How hard is walking? Not that hard for him. And this is a guy who dropped out of math, right? That's just, no, I'm done with that. Okay. Okay, so describe to me how to walk. Okay, so I'm standing here. We're gonna walk over towards that wall. You're gonna help me out here. This isn't math. It should be in your wheelhouse.
Put your left foot out
Okay, what's my left foot?
on your left side.
What's my left side? All right, so let's pretend we had that 10-minute conversation. So now I understand where my left foot is. Okay, I got my left foot. So you want me to put my left foot here?
Yep.
Okay, I did it.
Now do the same thing.
Okay, we're gonna assume we had the conversation about this right foot. So we had to learn about these. Okay. Okay. Now, when you said put my left foot here, what does that mean? What did I have to do?
Move foot.
Move my foot? My foot just starts to move. I seem petite, but in real life, I'm actually quite large. So moving my foot with my weight still on is going to be problematic. That's good.
Take the weight off.
Take the weight off. Okay, so we're going to have that 10-minute conversation about what weight is and all this stuff. Okay, now inside this leg, there's a bunch of muscles and stuff, right? Okay, so and you're firing different muscles. So when you're walking down that hall, you're thinking, okay, calf muscle, quads, and then all the fast twitch muscles inside there. You thinking about all those? Right?
No.
This guy's still stuck on fractions. Yes. What do you got that? Second grade? Right, fractions, second grade. Okay, so he's still stuck on fractions. Okay, and he thinks he's gonna tell me how to walk. And we got 4 zillion different muscles in here that what did we do? We when we were a baby, we eventually decided, hey, my legs are strong enough. I'm gonna pull myself up on this and get into some trouble. Right? And then the babies kept falling over. Finally, you figured out how, ooh. Like 2 days later, they're sprinting around. Speaking of sprinting, did you see the robotics Olympics? And we're going to be talking about a lot this semester because my background and stuff. Fastest man alive was Usain Bolt, right? Yeah, we have a robot that runs faster than him now. So a robot beat Usain Bolt in a foot race. There was robots running against robots. And the guy who won, the robot that won, beat Usain Record's world record in running. But they had to run like humans. It wasn't like he was just on roller skates like that Alita BattleBot movie.
BattleBot.
Yeah, that was a great movie. See, he understood that one. Anything with explosions, he's like, it's like, oh man, it's like RoboCop. You probably has RoboCops before you. Yeah, but yet these robots, they had to run like a person, so, but this guy beat Usain Bolt. All right, so we got robots that are, we're already building things. So those, does that robot, did a programmer tell that robot how to do this step and then this step with every little tiny angle? If you look back 20 years and you see robots and things like that they were trying to act human then, you would see them having these really clunky moves and stuff like that. But now with AI, things have smoothed out. They've effectively made robots learn how to walk just like people learn how to walk. Fall down, figure out what went wrong, make a little adjustment, try again. But it's not the programmer who's changing those things. It's the large language model that's running inside the robot's head that's controlling him that has decided, or maybe it's even a series of large language models. You got the big brain up here, and you got these little tiny, miniature chat GPTs at the joints or something, or maybe you just got one that's in charge of like the lower body or something like that. It's making all the calls about, okay, this muscle, or this servo or whatever robotic part it's controlling has to move in this certain way. So now all of a sudden we have these robots running faster than the fastest human who's ever existed. And, we can't necessarily explain how they run so naturally. They just do because we've put them into a situation and told them this is how you are to learn about this. Start running. And then they kept falling over and stuff. It is funny at the end of that race, these guys cross the finish line. They have one of those giant, like it's set up like an Olympic track and stuff. So everything looks legit. But at the end, they have like, they have guys just holding those giant gym mats. The robots slam into at the end. Then a whole bunch, and it's the Chinese who are making all these robots. So they're the ones who are way ahead of everybody else in robotics. And so then you have a whole bunch of Chinese guys run out there with like stretchers to haul their robot off the track. It's on it. It's on the internet. It's pretty entertaining. You can check it out. But the whole point of this is problems that we see as being trivial, like walking. When we really stop to think about it, we say, that's actually incredibly complex, right? And it's not even worth our full attention. We can text while doing it, right? And bob and weave out of people, around people while we're doing it. It's not even worth our full attention, yet we can't explain how we do it in enough detail to tell something else how to do it. Okay, so the real problem with becoming a good programmer is you have to train your mind to break problems down to tiny steps. And what does that mean? Is as a programmer, you will never be able to program a robot to walk like a human. There's just too many things going on there. Now we've seen that a large language model can be trained to do that because it's starting to operate more like us. So we're trying to operate more like a computer, but we're still thinking like a human. So we're sitting there at the keyboard. We have this language, just like we have a natural language, right? I'm speaking English. And, so you use your natural language, English, to tell people, you go do this, you go do this. Oh, this is how you build that thing. You give instructions for the things, but we can only describe stuff up to a certain complexity. Maybe a highly trained engineer or something like that can explain it in a little bit more detail, something like that. But no human being is going to have enough detail to actually reproduce a lot of the stuff that we do just naturally, just from practice and our brain growing. All right. So AI is attempting to, instead of us getting better, closer and closer to the computer, which is effectively the job of a programmer. You sit down as a human being who's used to talking to people, and now you're telling this guy what to do. And this guy isn't a people. I name them and stuff like that, but I also have dolls and stuff. So it's a thing. But in any case, I also have pictures of Mr. Gonzalez with his own airplane seat on flights. Yeah, it's bad. Yeah. Even I'm almost embarrassed by it. Just almost, not really. Okay. So when you sit down, you have to learn to talk to this dude, not a person, right? Okay. Although now with large language models, they're starting to become more like people. So everything is zigging and zagging now. But when you sit down and you're talking to this is not a person. You have to explain things to this guy in absolute detail if you're programming it to do something. Now, that means a couple of things. One, it means as a human being, we have to slow ourselves down and we have to relearn how to solve problems. We no longer can kind of just wing it. Okay. So, for example, those of you who are athletes who, play a game with, so you're playing a game with a basketball in your hands. So you probably are a pretty decent athlete at other sports dealing with, other ball sports and stuff like that. I know it might not look like it, but I played Division I tennis in college at University of Illinois, and then I broke my back. And that's when I got big. I was always a big eater. In fact, I've been on TV a zillion times. I was a professional eater, one of those guys that eats ridiculous amounts of food. My TV name was Awesome Fat. It was also the name of my first software company. So yeah, so after I broke my back playing tennis, I got fat because I used to eat just ridiculous amounts of food. But when we were playing 7 hours of tennis a day, it doesn't matter. That's why this guy's a rail. They have him running 4,000 laps. He's running up and down the court. He's trying to just push so much food and he just can't put on weight because he wants to be Shaq, right? Are you a center or are you like a forward? You're a tall guy. Small forward. All right, yeah. So once you get into the NBA levels, you got the freak shows there where he's short for almost a guard in the NBA. Like you see them, who we've heard of Steph Curry. Yeah. How tall would you say Steph Curry is?
6'2".
Yeah. Well, but he doesn't seem 6'2". You look at him like, oh, he's a short guy, right? When you're on the court, because he's surrounded by 7 foot tall dudes. Where most of us are shorter than Steph. I'm a little taller than him, but most of us are shorter than Steph Curry. We think of him as a little guy. So yeah. So I guess perception is kind of the thing. But what you're learning as a computer scientist is how to talk to a computer, how to tell a computer what to do, understand that computer at the level of zeros and ones. Which means you now need to understand, well, how do computers function? How do zeros and ones become this other thing, right? How does it turn into logic? So that's what we're going to be focusing on over the first bit of this course in class. You'll be going down more of a coding path through the book until those things come together, and then they'll be linked up. So kind of be prepared for that, because we need to retrain your mind. You're going to be doing that through reps from the book early on, and then learning why you're doing that in here. Okay, just like I said, those bad math teachers never told you why you're learning about tangent lines and areas under the curve. Because when you're a junior in high school, you don't care about areas under the curve. Even if they told you what it was for, you're like, I'm not going to need that, right? I'm not going to need that. Okay. Until later, and you figure out, hey, all these things are very important. In fact, all of our AI stuff today started off with areas under the curve. It's how they come up with a learning model for training large language models. Is if you think of this as the intelligence line and you want to put as much knowledge underneath that as possible, you want to fill that entire space. So, and then there's little angles between points in that thing. That is like a dynamic, it's called a learning coefficient, where you might give it more or less data during a certain period of training so that it gets closer and closer to maximum intelligence for that model. But it started with, oh, well, we need to know how much space is in here that we have to work with. How big is this suitcase for us to throw knowledge into, or for us to store the neural network that controls this AI stuff? So later on, there was a use for this stuff. But when you were learning about it in high school, you didn't care about any of that stuff, and your teacher didn't tell you about any of that stuff. So what's your motivation to learn the math stuff? it's hard, right? It's like motivation as well. I want to get a good grade. You know, guidance counselor says I need good grades to get into college, or whatever it is. Or mom and dad said I need to get B's or better, or I can't play sport X, whatever. All right. So I mentioned a few minutes ago that we're in a really exciting time. Like in many ways, I'm envious of some of you. Well, but really, it's kind of similar. I grew up during a very unique time in history, which is kind of where maybe I lucked out. Um, uh, there's a book by an author named Malcolm Gladwell. Any of you heard the author, Malcolm Gladwell? One of his books is called Outliers, and he talks about advantages. Now, so let me give you a couple of examples, and then you'll see where it connects back to this. All right, how many of you were familiar with the NHL, professional hockey? We know about those guys. Okay. Any of you hockey players in here on a team? Or okay. Well, that's good because they usually are not very good students. But would you believe that 80% of the players in the NHL are from Canada?
Yeah.
Yeah, it makes sense, right? That checks out. Would you believe that 80% of those people, 80% of those Canadians, were born in the first 3 months of the year? Why? So they have January, February, or March birthdays. 80% of the professional Canadian hockey players. What do you think?
That might explain why they like the cold.
Well, usually what do you get? You get people's like, well, when's the Stanley Cup, or the parents celebrating, you have you get what I'm saying. Without going into more detail. Really, when you look at kids under 10 years old, oh, you got something?
Oh, no.
Okay, it wasn't going to be good, I'm pretty sure. Yeah. Day one, it's bad. I'm a little bit different than your normal Concordia props. So, um, so when you're dealing with like people under 10 years old, and probably even beyond that, but like the difference between an 8-year-old and a 9-year-old in hand-eye coordination is significant. These are the years where you're kind of developing physically the most. So a 9-year-old is probably going to get more ice time, better coaching. It's going to make the traveling team, all these things because they just naturally have more hand-eye coordination than an 8-year-old just because of age. That doesn't mean there aren't outliers in those 8-year-olds and 7-year-olds, but generally speaking, the older you are in that young age group type stuff, the better chance you're going to have of getting more playing time. The age cutoff for junior hockey in Canada is in those first 3 months. So you're the oldest kid in the league every year during junior hockey. So you got more ice time, more playing time. You had the advantage of better coaching while you were growing up in those young years, that it set you then on a path towards something maybe that would be like the NHL. Keeping in mind that we're operating off of a subset of people who are professional hockey players, right? So these are all awesome hockey players, regardless, those 80%. And we're saying 80% of them were born in the first 3 months. Those people had the advantage of better coaching, more ice time, things like that. That 20% had to work for it, right? And so that's the explanation for that. All right, so here's another interesting one if you want to feel racist. So we're going to put 5 15-year-old American kids in a room and 5 15-year-old Chinese kids in a room. We're going to give them 7 numbers. They have to memorize those 7 numbers in 30 seconds. 100% of the Chinese kids can do it. 20% of the American kids can do it. Why?
How we're trained.
How we're trained? So the Chinese are just better than us?
Sometimes.
See, somebody will cut that out of the video. Lippman says Chinese people are better than Oh. All right. So no, it's not that the Chinese are better than us, as he suggested. What else? Why else do you think that the 100% of the Chinese kids can do it, but 20% of the American kids can do it?
Probably because they practice every single day.
Yeah, they didn't drop out of math.
Exactly.
Yeah.
How about a map? Yeah.
Yeah.
Exactly.
They practice every single day. Okay. Parents are stricter, the parents are standing there with baseball bats. Kid gets out of line. He's not putting in his 14th hour of the day working on his math homework. Beat down time. Yeah. Nope, that's not it either. Has nothing to do with biology or anything like that. The human brain is on about a 2-second loop, much like a video game. When you play a video game, things update. There's a game loop in all video games. And during each game loop, so maybe a game loop runs 100 times a second. So during that 100th of a second, a whole bunch of stuff in the video game has to happen. It figures out where all the different people are, things like that, and make sure that then gets distributed so everybody sees where your Call of Duty kill squad is and all that stuff. But you have this game loop. Humans, our brain operates on about a 2-second loop. Anything we can fit into 2 seconds, we can generally remember. The Chinese language, Mandarin, is more efficient when saying numbers than English is. So the Chinese kids could say all 7 numbers within 2 seconds. The American kids, English, they couldn't fit it. So those couple of kids that were able to do it, or I guess one kid that was able to do it, had to juggle 1 or 2 numbers across those 2 seconds because he had to use 2 brain loops to hold them. So it was the language. The Chinese kids, the way they represent numbers is just faster because of their language. So things like that, these advantages that exist. You still have talent, right? There are still those, hockey players that, they weren't born the first 3 months of the year in Canada, and they might be the best it's, ever played in the game or something like that. It's not that they can't do it. They just didn't have this extra little privilege, this extra little advantage, something like that. Well, all of you have this advantage when it comes to computer science because of the time period you're starting to learn in, where you're in a time period of AI and quantum, which is going to change the world substantially. When you graduate from college in 4 years, the world will be a very different place than it is right now. And you're going to be at the forefront of the people who are going to be controlling that world. But computer science has to change in order for this to happen. Similarly, I had an advantage. I was born in 1978. And 1978, we still had corded telephones. We still had the ones that were like this. We didn't have automatic car locks. We didn't have fuel injection. I grew up with all the older technology, but I also was at the learning age. So right around, I started programming when I was 9. So that would have been in 1987. So 1987, and this is in the very, very, very early days of when businesses were starting to get a single computer in the office or something like that. So my dad was a dentist. So he brought home, he had one of the first, computers in town that went into the office. So he brought it home, and of course, his little kid, me, took the entire thing apart first night in pieces. The computers were a little bit more expensive back then. So I think that computer back then was about $20,000. And this is $20,000 in 1987 money. And you got this 9-year-old who just tore it apart. I put it back together. Only had a couple of screws left. It worked. It was all good. But from that day forward, I kind of like fell in love with computers. And I grew up during a time where new technology from the base of where computers started kept being introduced to me. So I grew up at the same time as computers were growing up. So I had this advantage of effectively growing up with a best friend that was a computer. As he got faster and faster, and I got older and more mischievous and was overclocking these things. I had a buddy in college who lit his entire dorm room on fire because he was overclocking a 200 megahertz Celeron to 1.4 gigahertz. I know 1.4 gigahertz doesn't sound that fast to us. That well, actually, this has been grown out of us. How many of you actually know the specs of your computer? I know this guy does because you can see the back of his computer monitor. You know, there's some stuff going on there, so we have to chat anyways. But well, I work on a lot of research projects, and I get stronger students involved in those. So you guys could earn your way onto that, but I at least want to chat with him at some point. But so, anyways, I grew up in a very advantageous time where computers were readily available during their infancy, so I could see when things kept getting faster and faster and what changed and things like that. So I was very lucky. Now, I was also pretty intelligent. I have something called Asperger's, which is a form of autism, and I kind of hit the lottery. Usually, so when I was really young, I was like this awkward, kid. I wouldn't, who didn't really talk to people very much, was quiet. And I don't remember what happened, but at some point in time, I kind of embraced my eccentricity and just became this. And just decided, okay, well, I find this stuff interesting. Let's dive into it. And the things that I wasn't good at, because usually Asperger's is sometimes called savant syndrome. And usually what you have is someone who might be very, very good at like one or two things, and they're almost useless at a whole bunch of other stuff. I'm not completely useless at a bunch of other stuff, but I do need to. My wife has a shirt that says, I'm here for adult supervision for me. Um, but I kind of hit the lottery where all the things I like happened to be the things I was really good at. And the things I didn't, the things I wasn't good at, I didn't care that I wasn't good at them. But they produced this freak show that you have in front of you. But anyways, I had that advantage. You guys have the advantage of growing up right now is going to be, we're going through a shift that's greater than the internet ever was, greater than electricity ever was. I think we're going through one of the greatest shifts in human history right now with AI. And I'm kind of a little bit uniquely qualified to tell you that because of my research in quantum computing. So I have seen the fabric of the universe, how God built this world. And it is crazy when you actually get down into it. How many of you have heard of quantum mechanics? Okay, so quantum mechanics is like that's how we have redefined physics. All right, so you had classical physics, which was the way we assumed everything worked for a long, long, long time. And then all of a sudden we started messing around with subatomic stuff because at some point in time we thought the atom was the smallest thing. Well, now we found a whole bunch of stuff that's smaller than atoms. And how do we figure that out? This is going to be the evidence that we never grow past like being a 2 or 3-year-old. How do we discover that there are things inside of atoms? Splitting. Well, how do we split them? How many of you have heard of the Large Hadron Collider? You've heard the phrase before, maybe on a news story or something like that. All right, so and we're building some here. So what these are, they're underground tunnels, let's say. And they create a magnetic field and all this stuff. And effectively what they do is they take an atom of something, so some element, they take an atom, and they accelerate it as close to the speed of light as they can that direction. Take another atom. They accelerate it as close to the speed of light in that direction. They're both going through these loops over and over again, speeding up until they become they're going impossibly fast. And then they change the magnetic field just enough that they smash into each other. And they take a whole bunch of pictures and see what came out. This is the equivalent of a 2-year-old smashing stuff together because he wants to see what happens. That's our bleeding edge science, is we are smashing them together. But, we call it Large Hadron Collider because it sounds cooler than let's smash some atoms. Oh, yeah. All right, so that's how we have found these subatomic particles. So we keep discovering more and more stuff about the reality of our existence. Now, we're only going to see what God reveals to us, so we don't know how far this rabbit hole goes. The best understanding that we have of how science works, how physics works, is quantum mechanics. And so let me show you this video I like to show as my starting thing to give you an idea of quantum mechanics. How many of you have seen the movie Ant-Man? All right, so guy gets really small, right? And that gives him certain powers and stuff. But then you had that one where he went into the ultra small, right? Where it was going to be hard to come back to find mom and stuff. Okay, so think about that. We'll talk about this when it is over. It's like a 5-minute video.
The infamous double slit
Oh,
experiment.
I got
To understand this,
we got to see Superman in first.
oh, what they taught us in school isn't really the way it is. And that our senses are playing tricks on us. You just gotta wonder, what is this reality that we find ourselves in? Quantum physics says it's all just waves of information. Do I believe that? I hope so. Yikes! And here we are, the granddaddy of all quantum weirdness, the infamous double slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So when we throw things, that is matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, Maybe those little balls are bouncing off each other and creating that pattern. So they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron, leaved as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits and it goes through neither. And it goes through just one and it goes through just the other. All of these possibilities are in superposition with each other. Physicists were completely baffled by this. So they decided to peek and see which slit actually goes through. They put a measuring device by one slit, see which one it went through, and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of
All they
many.
did is measure. All they did
The
was
very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. It was here that physicists stepped forever into the strange, never world of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
So, pretty interesting thing there. When I first learned about the double slit experiment, it felt like where my head went first was it's kind of like God caught you with your hand in the cookie jar. So, to summarize what we just saw, if we're in the full-size world and I'm throwing tennis balls through those slits, it's hitting right on the other side of the wall, regardless whether we measure it, didn't measure it, whatever. But they also showed if you throw it in a swimming pool and push waves at it, the waves behave like that interference pattern thing. So we know waves do that second thing, and the tennis balls do the hit the dots on the other side thing. Shrink it down, now we have super tiny tennis balls. And when we shoot the tennis balls through, whether we're doing it one at a time or whatever, they're behaving like they're waves. So the tennis balls, when they're super tiny, behave like the water behaved when it was really big. And they're like, well, what's going on here? So they were wondering, are they smashing into each other or something? So they put a little device to measure. They didn't change the experiment at all. They just said they were looking, measuring. So don't equate measuring with looking necessarily. So they did that, and immediately the tennis balls started acting like tennis balls again, or the tiny tennis balls started acting the same way as the big tennis balls acted, just by measuring. That's all they changed. So the first place my mind went is that somebody's looking. Somebody's looking and he's been caught behaving one way, which was different than they behaved at the full size, and now they straightened up and started behaving the right way. That isn't actually what's happening. We can mathematically describe what's happening here. And it's actually the same problem we run into with quantum computers. How many of you have ever seen a picture of a quantum computer? All right, so you've seen it, all these tubes and stuff like that. Okay, what you're looking at is not the computer. Computer is this little tiny, it's a normal computer inside there, similar like what's in your iPhone, right? That's the computer. What you're seeing is refrigerant. So the issue here is that when they put that measuring device there, You probably heard him say something, it's a collection of potentials or something like that. And they mentioned a word superposition. Okay, so those two tennis balls, when they get fired, or one tennis ball, doesn't matter. When it gets fired at the quantum level, it's not just a 0 or a 1. It doesn't have a definitive direction at that point. It has a whole bunch of possible places. If we want to just think about it instead of direction, let's just think about it in terms of its destination, where it ultimately will hit on that far wall. So when you take that tiny tennis ball and you throw it, it has a chance, let's just say it's an equal chance of hitting at any one of those places on the wall. When we throw it at the quantum level, super tiny. But at the big level, it always hits in the same place on the wall. Something is occurring at the big level that isn't occurring at the small level unless we try to measure it. Right? So what does that mean? That means that something must be measuring it at the biggest level, even though we didn't intend to. Right? And what is that? It's the environment around us. We make, and so, but let's put this into something that would make sense to all of us. If I'm standing here and a student walks by this in this hallway next door or something like that, that person walking by isn't going to have any impact on us, right? The whole world's not shaking or anything like that. That's just no real impact. You might hear the person walk by or something, but it isn't really impacting our lives very much. All right. But now let's assume that we're an ant and the person walks by us. Our whole world is probably shaking, right? You know, a human walking by an ant is a major ordeal, right? You know, there's a lot going on there. So it really is that type of thing where we have these, we call them qubits in quantum computers. So a qubit is a quantum bit. In normal computing, we have bits, zeros and ones. And we're going to be talking a lot about bits over the next couple of weeks. Well, a qubit says, well, we're going to ultimately become a 0 or a 1. When all is said and done, this will be a 0 or a 1. But right now, we have a lot of different possible outcomes. So we put that, so what ends up happening is when that tiny tennis ball was first fired, it was in something called superposition, which means it was not a 0 or a 1. It had the potential to be either one of those at any point in time. Now, we saw in this experiment, maybe there was what, 8 or 10 slits or something like that. So to keep it simple, let's say there was 10 slits. When it first launched that tiny tennis ball, it had 10 different potential destinations. All right. So 0.1, 0.2, 0.3, 0.4, all the way up to 1. All right. So 10 different possible things that could happen, not just 0 or 1, not just 2 possible things, 10 possible things. All right. So it has those potentials. And as it's traveling through space, things have an impact on that microscopically. Really tiny levels of things, really tiny perturbations in the atmosphere starts having an impact on this that directs it to one of its 10 final destinations. And because what's inside of it shifts where there's a higher percent chance of one value versus the other value. So it kind of starts shifting its direction until it finally locks into a final thing, and then fires wherever it was currently traveling, something along those lines. The reason why we don't see that in our big life with the real tennis balls is because the entire environment around us is having an impact on us. And my research right now dealing with this, which coincides with Christianity and the Trinity, is the idea of what's called quantum field theory, that everything is a field and fields have impacts on each other. All right. So without getting into the science stuff of it, in this room, each one of us is a field and we have some sort of impact on each other, even when we're just sitting here, right? Okay. I mean, I will sense the fear of math coming off of him. He's like, I know, yeah, it's bad. Okay, so, but we all have some level of impact on each other, right? If you sneeze, everybody over there might look because it was a startling sound. You know, you didn't jump out of your seat, or unless the person's right in your ear and they have one of those really aggressive sneezes. My mom has one of those. It's terrible. You know, but we have an impact on each other's environment. Therefore, anything that would be in a state of potentials, like probabilistic destination, immediately flags. It becomes its final state basically instantly. So what happened at the big level with the tennis balls is as soon as we fired them, their state of potentials immediately became a 0 or a 1. Immediately collapsed to its final value before we ever could see it, because the environment caused it to collapse. Stuff around it was making the world shake too much that it caused it to fall apart. At the tiny, tiny level, you know, what they didn't talk about here, maybe he mentioned it, you know, they're doing that experiment like inside of a vacuum and stuff like that, really trying to turn the noise off to make sure they got the results of what happens if we just let it go to fruition, you know, without impacting it. But as soon as they put the measuring device, which is its own field, which has its own impact on the environment around it, it started behaving differently, and it started behaving in the position it was as it was passing through those slits, which means it started shooting right on the other side of those guys. And it's because that wave of potential, as he called it, the 90% chance of a 1 versus a 10% chance of a 0, that's a wave that kind of maybe describes that at any point in time as it moves its chances of a 0 or chances of a 1 up or down based on what's happening in the environment. Then it ends up finally collapsing, and it's kind of like, you know, if you have something in what's called the coin flip state, superposition, if you had 100 qubits and you measured all 100 of them, you'd have roughly 50 zeros and 50 ones. Because there was a 50-50 chance of a 0 or 1 in its initial state. But as that thing's flying through the air, those percentages could be shifting based on little perturbations in the atmosphere and stuff like that. So maybe it becomes a 60% chance of a 1 versus a 40% chance of a 0, so on and so forth. In fact, all our quantum algorithms operate on that. They create little tiny perturbations on these qubits that are still in superposition to make them a little bit more likely to end up being a 1, or a little bit more likely to end up being a 0. You know, they make little tiny chiropractic adjustments on it, just enough to nudge it without breaking it, without measuring it. And that's the kicker, is how do we quantum computing, in order for us to use those values for doing computation, we have to be able to rely on them holding together until we measure them, right? But because we're leveraging them to solve a problem, whatever the problem that we're, you know, is, because we're leveraging them, we are trying to make little tiny changes to them based on a quantum algorithm that probably some mathematician came up with. For example, there's a famous algorithm. Any of you ever heard of something called Shor's algorithm? Shor's algorithm is really fun for describing the power of quantum and where we're going in this world during this next 4 years of your life. And this actually became a real reality in the last 6 months, and nobody actually heard about it, except the people on the science side of this. But so Shor's algorithm, how many of you have ever seen something on your phone or on a web browser or anything like that that says RSA security? So most of the encryption algorithms we use today, like your banks and all that stuff, use something called RSA. All right. So RSA is an encryption algorithm that is trying to protect your passwords and your banks, and people can't get into your stuff, right? All right. So, and now, we've seen a movement. I'm sure you've seen it over the last couple of years of movements towards multi-factor authentication. You got to put your face here, fingerprints all over the place. At what point are they going to be doing blood samples? Who knows? But that's going to become less funny after you hear the punchline of this thing. All right, so we have multiple ways of securing our stuff now, but RSA is it started with math. The idea is you take two big prime numbers. So a prime number is a number evenly divisible by only one in itself. There's a couple of little nuances there, but let's just say that. Take two giant prime numbers, you multiply them together. That gets you a key. So that gets you another giant number. The security of RSA is based on how long it would take to factor out those two original prime numbers. So we take the two prime numbers, we multiply them together, we get a new number. RSA's security is based on how long would it take for us to find those original two prime numbers that we multiplied together to get this giant number. And depending on how you're looking at doing that experiment and things like that, the answer is somewhere between 200,000 and 3 trillion years using what's called 2048, RSA 2048, which is kind of our higher encryption. So that means we use 2048 zeros and ones to represent this giant number. So that's 2 to the 2048th power. That's the number of unique keys that you can have in that. That's a lot. That's a big, big number. Like it's one of those, you put it in your calculator, it's going to say E with a whole bunch of numbers after it. And it's not a number for us. It's just huge. So if you were to write a normal computer program that literally tried to test each, you take two different numbers and you just walk through the primes and you multiply them together until you get this giant number and you have to just start from each side. Depending on the amount of computing power we assume you have access to. So if we pretend like we can link every single computer on the planet and we can link all of their memory, so we can remember, so basically our ability to remember stuff is at the planet level. All our computers, we connect them all together so we have all the memory on the planet. That's where they get to that like 200,000 year number. But if you're using like a supercomputer or something like that, we're talking 3 trillion years. Really long time, right? Do you feel pretty secure in your bank password if you knew that it would take someone 200,000 years to crack it? You're okay with that at this point, right? All right. Now, a quantum computer running Shor's algorithm, a stable quantum computer. I'll come back to that in a second. Hold on, where are we at on time? Okay, for 3 minutes. Another thing, I get going on stuff. So if I always set my alarm, so my alarm will go off at 9:20. But if I ever go past and forget to set my alarm, just tell me to shut up. I'm not a formal person, so you don't have to. Just whatever. Just say whatever to get my attention. I'm not going to be offended. All right, so it doesn't have to be Mike, whatever. I don't care. It's always weird when like faculty like correct you. Oh, it's Doctor Professor.
You're another person.
You're another person. Okay, fine. I know more about computer science than you guys do. He knows more about basketball than I do. That's why we had that guy, Dr. J. Called him Doctor. Yeah, we're just another person. In fact, I don't like the fact that I have to put pants on. It's the first time I've had pants on. Well, I mean, I wore shorts. My PE teacher said he doesn't wear pants. Yeah, this is the first time I've had it on since last day of school last semester. And I attended 2 weddings. That's how bad the dress code is. Any case, with a stable quantum computer, whatever that means, and Shor's algorithm, we can crack that same password in, let's call it roughly 8 hours. 8 hours versus 3 trillion years. That's the power quantum brings to the table. Now, the thing that we are struggling with, I said a stable quantum computer, is remember that tennis ball that had the chance of a 0 or a chance of 1 until we measured it? Well, we're trying to build quantum computers where this guy doesn't get accidentally measured by whatever's happening in the environment around it before we're ready to measure it. So that we could do all our little quantum adjustments. They're quantum gates is what we call them inside of a quantum computer. These tiny little chiropractic adjustments to it without it collapsing to a 0 or a 1. We don't want it to collapse too early. But the challenge for us is we have no way of knowing if it has collapsed. Because it's a 0 or 1 here, or it's a 0 and 1 300 instructions later. We don't know where that 0 and 1 started. Did it live up to our final measurement, or did it collapse way early? Don't know. So we have to have a way of holding it together long enough. So punchline, and we're out of time, is and make sure you go to the site, you look at the textbook, and you start working through the textbook. You'll see the steps up there. So check Canvas today. But I was mentioning with the quantum computer, that refrigerant stuff, we are trying to drop them down to close to absolute zero to keep the amount of environmental disturbance to almost nothing, and it's still not good enough. Yet in the last 6 months, we've gotten something to hold stable long enough, just long enough, to do something where we're calculating eigenvalues. With any of you who had linear algebra might remember that term at some point and said, oh, well, what am I learning this for? Eigenvalues are used to calculate the location of an electron in a molecule so that we can simulate molecules before, like, medicines go to clinical trial. So instead of a clinical trial lasting for 7 years, let's say, and costing zillions of dollars, you and the scientists going through 200,000 permutations of a molecule, we can now have a quantum computer narrow down that 200,000 down to the most promising 12. Hand that to the scientists, and now the scientists can come up with, you're going to see cures and new medications in the next 2 years that are going to, things are going to be cured that were never cured before. This is the most exciting time in history right now, and it's happened in the last 6 months. With us being able to model things where we don't have enough computation power on the planet to even try doing that. It's happening somewhere. Must be evolution. All right, I will see everybody on Thursday. Make sure you check out the book on Canvas and start working through that. And we'll keep chugging in here. Questions, comments, concerns, bribes?
You not put math to this?
The math is all over the place. I'm actually going to put extra.
I tried. You can't say that I didn't try.